Welcome back. All right, so this will be the final video of this unit, and this is going to cover empirical and molecular formula. Okay, so empirical formula we'll go over first, but the empirical formula just gives the simplest whole number ratio of the atoms or moles of the elements in a compound. Right? The empirical formula is basically what you would consider the chemical formula in 95% of the cases so far. Right? Empirical formula. This is an empirical formula, NaCl. This is an empirical formula, H2O. It's the ratio in which these materials combine. Sodium chloride means that you get one sodium, one chlorine. That means that it combines a 1-to-1 ratio. The empirical formula for water means that for every 2 moles of hydrogen, it combines with 1 mole of oxygen. Okay? And so what we're going to be doing is just knowing that you can, if you have percent composition data, you can determine the empirical formula of a compound. So, the steps. If you're given percent composition, just assume you have 100 grams of that compound. Because if you have 100 grams of that compound, then the percent composition, those values just become how many grams you have of everything. If you have mass that's of all the parts of the compound and it's given, just use those numbers. But if you were just given percent, just assume you have 100 grams of compound to make the numbers easy. Then we want to change the mass to moles. And then the next step is you divide all the numbers of moles for each of the elements in the compound by the smallest number of moles, because one thing that you know about a chemical formula is, right, all these coefficients, whether this is assumed that's a 1 and it's a 1, these are integers. So we have to make sure that they're integers in our empirical formula. And the way that we do that is that you divide the smallest number of moles by, everything by the smallest number of moles, and so something's going to be a 1 and everything's going to be some thing from that. Then this can be the possible tricky part, is that when you get to the number of moles after you've done step 3, if not all of them are whole numbers, then we have to figure out how we can make them whole numbers. So if something ends in a 0.5, one way to get rid of that is just multiply everything by 2. Something ends in a 0.25, well, we're going to have to probably multiply by 4. If it's 0.33 or 0.66, right, these are thirds. That's 1/3, this is 2/3 equivalent. Well, you're going to have to multiply by 3. And that will make more sense when I do an example or two. And then once you've made sure everything is a whole number, then you can write the empirical formula, which basically these are just the subscripts in the chemical formula. Like I said, like H2O, right? There's a 2, and right, this is a 1. We just don't happen to write ones. So, first example. Compound is analyzed and found to contain this mass of calcium, this mass of oxygen, this mass of hydrogen. What is the empirical formula? Basically, it's like, hey, what is the chemical formula of this compound based on these masses and how they combine? So first step, got to convert everything to moles. So we take the mass that was calcium, 13.5, divide it by its mole mass, 40.08 grams per mole for calcium. Do the same thing for the oxygen, 10.8 grams of oxygen divided by 16 grams per mole for the oxygen. And the same thing for the hydrogen, 6.675 grams of hydrogen divided by 1.01 grams per mole hydrogen. So if we divide just from a unit perspective from this work, right, we're taking grams and dividing it by the molar mass, which is grams per mole. Grams divided by grams per mole from a unit perspective, right, that cancels with this. We are left with 1/1 moles, which is just a very difficult way of writing moles. So, put these values into a calculator. Got 3 sitting figures here. For the calcium, so that's 0.337 moles. Do the same thing with the oxygen here. we get 0.675 moles. Do the same thing for the hydrogen with 0.668 moles of hydrogen. Right, if we were to stop here, what this tells us is that our chemical formula we'd say is Ca 0.337, and then O 0.675, and then H 0.668. Right, and that doesn't make make sense because we're not used to seeing anything but integers here. So to make things in an integer, we look at this, which one's the smallest. Hopefully we can agree that this one here is our smallest. We are going to divide all of them by this value. So this becomes a 1 because it's divided by itself. 0.675 becomes 2. And this is 1.98, which is close enough we can round it to 2. Okay, you notice it was not one of these values, or close to one of these values. We'd have to do something about it if it was. But 0.98, you know, if we're pretty close to an integer, we can just round it to that. So what this tells you is the chemical formula CaO2H2. Or what you might notice, wait a minute, this looks familiar. That's calcium hydroxide. And just realized I did this step, divide each mole by the smallest number. Well, this was done here, and then this last one was there. So it's, okay, I'll just rewrite this. CaO2H2, which you would recognize as calcium hydroxide. We do this next one. Empirical formula of the compound that's 25.9% nitrogen and 74.1% oxygen. Again, we are given percents, not actual masses. The hint to make your life easier is just assume you have 100 grams. You have 100 grams of the compound, that means 25.9 grams of nitrogen are present and 74.1% grams of oxygen present. So we've got nitrogen, 25.9 grams. We need to convert that to moles and do the same thing for the oxygen. So 25.9 grams divided by the 14.01 gives you 1.85 moles of nitrogen present. And the oxygen, 74.1 divided by 16 is 4.63 moles of oxygen. Now again, we've got to divide both of these by the smallest, which is this. Divide that by more than that. Divide this by the same thing. That becomes a 1. This becomes a 2.5. So this would seem to suggest that our formula is NO 2.5, which is not correct. Remember, these things have to be integers. And this is too far away from, you cannot round this down to 2 or round this up to 3. Remember what we talked about up here? If it ends close to 0.5, we multiply everything by 2. So that means this gets multiplied by 2, and this gets multiplied by 2. That's a 2 now, and this is a 5. So our empirical formula is N2O5. Okay, so that's empirical formula. Now, let's talk about molecular formula. So the difference between empirical and molecular formula is that the empirical formula is the simplest ratio. Okay, what that means is, let's say, you've had a compound that was we've got this compound ethane and an ethane, methane and ethane. Actually, no, that's not a good example. Just ignore that. We'll come back to that. But molecular formula, it gives you the actual number of atoms of each element in a molecular compound. Molecular, right? Typically, 90% of the time, this is talking about covalent. Only in a few cases will an ionic compound have a molecular formula. But the relationship between a molecular formula and the empirical is that the molecular formula is always some whole number multiple of its empirical formula. Okay, for example, in the last problem, when it was N2O5 was the empirical formula, well, it means that if this is the empirical formula, you could have a compound N2O5, you could have a compound that shares this molecular empirical formula, but just a multiple 2 of it, like N4O10 or N6O15. Right? These 3 compounds here would share the same empirical formula, but they would have 3 different molecular formulas. Right? This is basically, this formula represents this empirical formula multiplied by 2. This is this empirical formula multiplied by 3. So that's what this talks about, whole number multiple. So in order to do a molecular formula problem, you need one additional piece of information typically. You need to know probably what the actual molar mass of the true compound is. Without this piece of information here, and you would only be able to figure out what the empirical formula is. Because in order to go from the empirical to the molecular formula, you have to be able to determine this whole number multiple. But in order to find the molecular formula, you need the empirical. So you have to start there. This one was given percents. So remember, when you're given percents, you just need to find, just assume you have 100 grams of that substance. That means if you have 100 grams of the substance, you have 40.0 grams of carbon. And we want to convert that to moles. You have 6.67 grams of hydrogen, convert that to moles. And you have 53.3 grams of oxygen, and you want to convert that to moles. So you divide it by its molar mass. 40 divided by 12. So that represents 3.33 moles of carbon. 6.60 moles of hydrogen. And 3.33 moles of oxygen. Now we've got to divide by the smallest value, which happens to be shared by carbon and oxygen. So we're going to divide everything by 3.33. So that's a 1. This is a 1. This comes out to be 1.98, which is close enough that we could just make it a 2. Around that. So the empirical formula is CH2O. Now, we need to find that whole number multiple of what the empirical, the molecular formula is. So in order to do that, we need to determine the molar mass of the empirical formula. So CH2O, the molar mass of this. So we got 12 grams for the hydrogen, 12 grams carbon, 2.02 grams hydrogen, and 16 grams oxygen. That's roughly 30.03 grams per mole. So we'll just call this the molar mass of the empirical formula, molar mass E. So now we just need to compare this molar mass to the actual molar mass. Well, actual molar mass is 150. So that multiple, I'm just going to No, I'm not going to call it N because N is a symbol for moles. I don't want to confuse anyone. But you're just going to take the actual molar mass divided by the empirical molar mass. And 150 divided by 30.03 is basically 5. It's 4.995. This number here will, if you did it correctly, will always be basically an integer. It's not, you won't have to do anything like this for this whole number multiple. But knowing that, take this multiple and you just take the empirical formula. So we're just going to take the CH2O and multiply everything by 5. So that means that becomes C5H10O5. So that would be the molecular formula of ribose. All right, and then here is a different style of problem you might run into for molecular formula, which is much easier because it tells you the empirical formula. Empirical formula is CH3. And it tells you the actual molar mass is 30. So the only step you have to do is that final one from the last problem is like compare. We have to figure out what the molar mass of the empirical formula is, which is 12 plus 3.03 for the 3 hydrogens, that's 15. And to find the multiple, we take the molar mass, the actual, divided by the empirical molar mass. And you get a value of 2. So 2 times each of these. So our molecular formula is C2H6. Those type of problems are much simpler because you don't have to find the empirical formula because there's already